Welcome to Control4 Driver Development Essentials. My name is Peter Casenza. In this video, we'll begin to look at how the data passing through the Control4 driver architecture needs to be handled in order to successfully meet the needs of command and notification functionality. Throughout the course of these training videos, we've often discussed data moving from the proxy layer to the protocol and vice versa. There are several important concepts that need to be considered when discussing how this data is stored, accessed when needed, parsed, and finally executed. This video will focus on managing data effectively in tables, as well as calling that data within a device driver. As a driver writer, one of the more complex tasks you're faced with is making sure your driver handles data in an efficient manner. Lua, the scripting language used by DriverWorks, is a table-focused language that allows you to store data as well as functions within tables. This makes for a very flexible, powerful, and useful environment when it comes to data management and execution. While this training module explains how data is handled within the Control4 architecture, it is not intended to be a Lua training exercise. It makes the assumption that you, the audience, possess a level of Lua knowledge. If you would like to learn more about Lua, the Lua reference manual and other information is available at lua.org. Let's start by looking at how driver data is stored. As mentioned, Lua is a table-focused scripting language. It's very flexible in that it allows you to store not only your data in tables, but functions can reside within those tables as well. Additionally, tables can be stored within tables, and all table elements can be indexed. So you see, tables in Lua are very powerful elements. Let's take a look at several tables that have been created to store data for a receiver driver. The first one is a simple table called T-Output Command Map. The purpose of this table is to define the protocol syntax elements for audio-video zones. When you think about most receivers, they typically support multiple zones of distribution. Our receiver supports two, a main zone and a secondary zone. Here is the table that handles these two zones' syntax elements. This table has two values, P1 and P2, which are indexed as 0 and 1, respectively. You may be wondering how the data to populate this table was obtained. If we look at the receiver's protocol document, we can see that they have defined Zone 1 and Zone 2 values for us. Using this information, we've created a table that associates the receiver's Zone 1 value, P1, with an indexed value of 0. Likewise, Zone 2 is associated with an indexed value of 1. You'll notice the S used in the commands above. This is a convention required by the device protocol. While we've omitted that in our table, you'll see in our example code exactly where the S is handled. Now, let's look at a table that is somewhat larger. This table is called T-Input Command Map. Like our other table, it associates an index with a predefined value that our protocol documentation provided. For example, input BDP is an index for an entry that we have added to the table. We have entered a value of 1 for this entry. The value of 1 is based on the definition in our protocol documentation for the BDP input. All of the indexed values are input names that we have defined in the connections area of our driver's XML code. For example, here is the XML connections code for input BDP. At this point, we should discuss a convention that is typically used throughout Control4 DriverWorks drivers that involve AV connection ID values. AV connection ID values are often modified from the format they are entered into the XML to the format they are ultimately used inside of functions and commands. The reason why we make this modification goes beyond the scope of this module. For now, just know that there's a logical reason why we're doing this, and also know that these types of topics will be covered later in the T-Series training modules. If we look at the XML code, we can see that the input BDP ID value is 1002. We need to modify this value using the modulus function to remove the thousands value from it. This results in a value of 2. This is an important concept to remember and comes into play when we look at our next table example. It is also important to remember that the numerical values assigned to each of the input types in the T-input command map table come from the receiver's protocol document. If we look at the document again, we can see the values the receiver uses when handling input changes. Now, let's take a look at a table that is somewhat more complex. This is the T-input con map by ID table. It associates an indexed value with an input connection name, along with that input connection's binding ID value. This is an interesting table because it is actually several tables within a table. Let's look at one line of the table to get a better understanding of what it contains. Upon review, we see that this entry deals with input BDP. The first element is an index with a value of 2. Again, this value comes from the XML portion of our driver, where we've defined connections. Remember earlier when we talked about the need to modify the XML value using the modulus function to remove the thousands from the ID value? Here, the modded value for input BDP is used as an index. We went from a value of 1002 to a value of 2. The elements following the 2, in brackets, actually make up a table of their own. They contain an input name that we've defined in our XML as well. Along with the input name, our table also provides us with the binding ID value for that input. We've discussed binding IDs in previous training modules, but to reiterate, a binding ID is a value assigned to an input and associates that particular input with a proxy. For example, we have a binding ID for our BDP input associated with the receiver proxy. Likewise, we have a binding ID for our AM antenna input associated with the tuner proxy. In this case, we've associated an indexed value of 2 with the input named input BDP and its defined binding ID. Based upon the information we've defined in these tables, we can construct a command string that adheres to the syntax detailed in the device's protocol document. In our example, we are building a command that would select the input BDP in the main zone. Here is the code from our driver that builds this command string and stores it in a variable named command. It uses an output value from the T-output command map table, followed by an S, which is a requirement of our receiver's protocol, followed by an indexed value from the T-input con map by ID table. This indexed value will reference the name of the input from this table with the indexed value assigned to that name in the T-input command map table. Based upon how we've indexed these values in our tables, and the device protocol requirement of S to separate the elements, the function, when executed, would work like this. In this example, we know that 0 has been indexed as our main zone, so T-input command map 0 would give us a value of P1. 2 has been indexed for input BDP, so T-input con map by ID 2.name would give us a value of input BDP. And finally, T-input command map indexed with the value input BDP would give us the value of 1, which is what we ultimately need for the input selection command we are building. So, this code would return a command string of P1S1. Let's look at another example of using the data stored in these tables to execute a command. Consider a scenario where our receiver driver has been successfully included in a Control4 project. A user approaches a touchscreen and wants to switch their AV system over to use their Blu-ray DVD player, which is bound to the input named Input BDP. When they select the Blu-ray DVD icon on their touchscreen, an input command is sent from the UI to the proxy. In turn, the proxy needs to tell the receiver protocol driver to change its input to Input BDP. It does this using a predefined command called setInput. The setInput command is delivered to the protocol within the Receive from Proxy API. It is defined in our driver in the code section designated for all of the commands that the protocol will receive from the proxy. Here is the Receive from Proxy, and if we scroll down, we'll find setInput. A prototype of the setInput command looks like this. When populated with schema, it looks like this. As you can see, the setInput command returns two parameters: the binding ID of the input that is being set and a table of parameters. The table of parameters is a table that includes indices of the input and output participating in the input selection that is in progress. Once again, we're seeing an example of connection ID values being modified using the modulus function to remove the thousands. You'll notice the two lines below the function for local input and local output. These lines are there to modify the connection ID value and store them in local variables to be used further on in this function. If we look at our connection XML, we can see how our table values can be used to set our input to play the Blu-ray player in the main zone of the receiver. Here is the connection XML code for the main zone. As you can see, it has an ID value of 2000. When we modify this value by removing the thousands value, we are left with a value of 0. That value, as indexed in our T output command map table, is for our main zone. Here is the XML code for the video portion of the Blu-ray AV connection. The 1000 range of connection IDs is reserved for video connections. Again, after we modify the value of 1002, we are left with a value of 2, which is our input BDP index in the T-con map by ID table. Finally, here is the XML code for the audio portion of our Blu-ray AV connection. The 3000 range of connection IDs is reserved for audio connections. And again, we'll modify the value of 3002 and be left with a value of 2, which is our input BDP index in the T input con map by ID table. After watching this training module, you should have an overview of the concepts behind storing driver data in tables. Storing data in tables and understanding how APIs and functions are used to call that data are extremely valuable advanced level driver development skills. Now that you have the overview information behind data and table relationships, we recommend viewing the next training video, which deals with parsing data and queue management. There we will dig even deeper into the driver schema and review examples of data before and after parsing. We'll also look at ways to use queues to marshal commands being generated in your driver.